Okay. Right. So this thing estimating the different parameters. Did you share this PDF? Yes, Mohit. It's there on Google Drive. I just changed the numbers and everything on Google Drive. 1, 2, 3, 4, 5 like that. Okay. Sure. Right. So the second part is like you have the data, but you can't have the whole population of data, right? You can have a sample of data. Then what will you do in that case? So you can't know the exact mean or any parameter, let's say mean, median, or anything, right? Variance or anything. So how can you then estimate very properly, right? It's nothing but the second part. There will be saying this CLT, central limit theorem, beautiful one. Then confidence interval, like what is the confidence interval, like in which interval you can confidently say like your particular parameter would be there. And by means of parameter, it can be mean, median, or anything that you want to predict, right? Then we will say some Chebyshev's inequality and bootstrapping, and the modern technique, you can say. And then the last but not least is how can you compare the relationship between two random variable in your data? It is possible that it is collinear, right? Or sometimes you want to see like if the data is like if the two random variable or the data is following the same distribution or not, in case of that train and test case, like that. Correct. Then what you will be doing? Then you will be applying this case test, then covariance, and due to some problems in covariance, we will use PCC. Then modified version of that SRCC, say Spearman, rank correlation coefficient, and some miscellaneous topics. Right. So let's start with the first chapter. That's nothing but the observing and transforming the given random variable. So the first and foremost is is skewness and kurtosis. Why it is useful and what is measure, what does it measure? So skewness is the measure of asymmetry of probability distribution of random variable about its mean. That means given a mean value, or you can say average value, how the values are deviating, right? If it is like deviating on left side more, on right side more, like that. In case of normal distribution, there won't be, you can say, it would be a symmetry around the mean, right? So if I take a simple normal distribution, then on if you put a mirror on mean, then you will have the exact symmetric data around the mean, right? So this would be nothing but the normal distribution, simple normal distribution without and it is symmetric about its mean. But in case of this negative skewed data or positive skewed data, it would be something like this. Around its mean, it's not symmetrical. It is something like this, right? Or in case of this negative skew, it is something like this, right? And why it is called negative skew? So on the left hand side of mu, we call it a negative side. On right hand side, we call it a positive side. So the skewness is you can say like how much tail you have on the negative side. So it is the negative skewed data, or you can say right leaning data, right? Why it is left skew? Because we have the skewness on the left hand side of the mean. And similarly, we have right skew, or you can say positive skew data. This is the measure of skewness formula. No need to remember, but I just put it for reference. Correct. The next kurtosis is nothing but measure of the tailedness, right? It is not measuring the pickedness. In first, you can say moment, you will think like it is measuring how picket data is around the mean, but it is actually measuring the tail, how much tail you are having, how tailedness you have this distribution in the tail. It is measured by the kurtosis, right? And by, you can say, convention or something, by convention, we are comparing everything with the normal distribution. So we have this excess kurtosis. So excess kurtosis is nothing but kurtosis minus 3. And what is this 3? 3 is nothing but if you put the value of normal distribution into kurtosis formula, you will get 3. So now what we are doing is, given a data, we calculate the excess kurtosis, and it is defined as kurtosis of a given data, or you can say distribution minus 3. So we are comparing it with the Gaussian distribution. and 3 is nothing but the Gaussian RV kurtosis, that means Gaussian random variable kurtosis, right? And this graph is for excess kurtosis, not kurtosis, right? So you can just add 3 and you can get the kurtosis. And if you see this black line, let me zoom it a bit. This black line is presenting my normal distribution. N is nothing but the normal distribution. So excess kurtosis is 0. Why? Normal distribution kurtosis is 3. 3 minus 3 is 0. As you go like this red, you can say distribution, it is nothing but the Laplace or double exponential kurtosis, right? So if you take any side of it, it is having a larger tail. See, here the red goes and here I have this much of a tail, right? So there is a very much, you can say, tailedness, right? So that's why it's having the highest, you can say, excess kurtosis. So a kurtosis for this Laplace or double exponential is 6. 6 minus 3, I guess 3. And as you go like more, you can say less and less tail. So at normal you get the 0. Then this is C is for, I don't know, race cosine distribution. This the example is taken from the Wikipedia. And if you take the uniform distribution, do we have any kind of a tail? No, right? Then the excess kurtosis is minus 1.2, right? So less and less tail you get, less and less value of kurtosis you get. And this is majorly useful to calculate this thing, outliers, right? And one example is also given on Wikipedia if you are interested.
Uh,
So yes.
Mayur, when we sorry to interrupt. When we I mean when for normal distribution, that pink line kurtosis would be zero, right? No, sorry,
Kurtosis would be
black
3.
line, black line,
Kurtosis would
normal
be 3.
distribution. For normal distribution, it would be three or it would be zero.
3, 3. Excess kurtosis would be 3, 0. Right. So excess kurtosis is nothing but how much excess kurtosis you have with reference to normal distribution with respect to, right. So and the kurtosis for normal distribution is 3.
Okay, okay.
Correct. That's
And
why
what is
3
the use?
minus
I
3
mean,
we are getting 0 here.
what is the significance of kurtosis, if you know actually?
Huh?
What is the significance of kurtosis?
See, kurtosis is to measure this kind of a tailedness, like how tailed, like how much tail you have in your data. Right. So if you compare this red with this, you can say this blue one. See, this blue has really, you can say small tail, right? But this red is the bigger tail. After one, you can say it is the tail started or 1.5, right? And it is useful to calculate the kurtosis, this outlier also. One simple example is given. Using this formula, we calculate this kurtosis. Sorry, I guess this is the modified formula. Okay, so if we have this kind of a data set, everything is like lying between 0 to 5, but there is one outlier 999, right? So if you calculate this Jedi value, I am not sure what this Jedi value is. I guess this is standardization. Yes, standardized data. And now if you calculate Jedi 4, I guess this is now useful in calculating this kurtosis. Right? In formula, we are using this. So after calculating this Zi for value, you can observe that this kurtosis, the overall kurtosis value is due to this number 36964, right? So we can basically actually we can find out the outlier using kurtosis. Okay. And there is a trick basically. It is very deep. They use this mean value and the kurtosis value, and there are some formulation to detect like if there is a very high number or something like that. Correct. But see, this is not, see, every time we cannot print a data and see like what's happening and like that. So we need to formulate them somehow, right? And to generalize it, it is never easy, or you can say straightforward formula or mathematics, because we are not even plotting a graph and using this kind of a formula. The skewness formula in kurtosis is bigger than that. We can directly identify like how much pickedness, not pickedness, the tailedness of a data is, right?
So basically, the tailness of the curve tells you like how variety the data is, right? So maybe that will help you. I think that's the main point, I guess.
Correct,
Like
correct.
if you have that the tail is too, what you say, too big, maybe you
Hmm.
have a long variety of data. So for normal, everything will be at the center, right? Mostly.
Yes, yes.
Other two sides, it will be less. But if you look at the other curves,
Hmm.
you will have little bit peakness towards the left and right. So it might help us to find out the like how what is the variety of data that the distribution has. Maybe I might be wrong. Correct me if I'm
Correct,
wrong.
correct. No, no, no. I completely, yes. That's correct understanding. Right, normal distribution, why we are comparing it to a normal distribution and why we are measuring this tailness, right? So if tailness is very much like this kind of a double exponential data, right? So in case of even exponential, what's happening is most of your data is around mu, right? In like you will have less and less. Just a second, guys. Huh? I just got to go. Okay. So, in case of exponential data, we saw those kind of you can say example that you will have less and less number of oil field, large oil field, right? Where the value is high. Sorry, this side, but there would be many very much you can say small oil fields, right? So the number of smaller oil field would be larger if you follow these red graphs, and the value of the larger oil field with the millions of barrels of oil, it would be very less the probability, right? So you definitely you can use this kind of kurtosis and you can find out like how the data is distributed, correct. Okay, with that let's jump on to next topic. That's nothing but
And
hello.
one more thing. What is the difference in uniform and normal distribution? Actually, I have not gone through the videos properly.
See, uniform means the probability of getting any value of x. Just a second, guys. Why I'm getting this much of Flipkart code? Hmm, just a second. कोई booking करा जाए? Just a second, guys. I just got 10 or 20 or more than that number just right now.
Flipkart codes, OTPs.
Flipkart, Byju's, then Mfine, House, Housing.com, Just DI. I don't know what is this. Oh my god, they are still coming. 2, 3, 4, 5,
किसने
6,
डेटा
7,
चुरा
8.
लिया तुम्हारा?
This is data science.
1, 2, 3, 4, 5, 6, 7, 8. Byju's, I am getting so much. Okay, crad. Array, yaar. What is this?
They must be asking for you to have a teacher like you.
OTP, I am getting.
Looks like I can. Mayur, it's try to block the user ID for some time.
I don't know. On my another number, I am getting array, yaar. It's
Okay,
it's
but
now 15.
that
Let
that might be
me.
mapped to some bank account, right? If you
No,
try
no, it's
create,
not mapped.
then it is fine.
It's a WhatsApp number and it's not mapped with bank account. Okay, please.
Maybe it got hacked. Your number.
It's BSNL. We can't comment.
Yeah, yeah, it usually happens. Like I have an BSNL number. It usually happens.
Okay, now see, I got one story, then I got from Redbus, one is from Byju's, okay, credit. Every company is trying to make account on this. Okay, let me turn off the card.
I am
Actually,
also
it's
getting the messages. Domino's Pizza, Oven Story,
oh my
Flipkart,
god,
something like that.
is phone pay missing or something or what? Oh, ho, ho, ho. Okay, I just turn off that card. I actually there is no meaning to take that card. It's very old. That's why I'm keeping it like old friends might have that number. Okay, now it would be silent. Okay, let's have the next topic. Okay, QQ plot, right? And why this QQ plot is basically useful. I haven't used it personally yet, but this is useful to calculate to actually identify if your data is normally distributed or not, right? That okay, I was explaining this uniform distribution. Yes, so uniform distribution is nothing but if you see over all the value of x, the probability is similar, right? So uniform distribution is like probability of happening any random variable, any value of random variable is similar, like throwing a dice. 1 2 3 4 5 6 all has the similar probability. And normal distribution is most most you observe in the nature, that most of your data is is around the mean, right? As you go far away from the mean, the probability of happening will you can say will be very near to zero after 3 sigma range, right? Okay, let's see like what QQ plot is and how to get that, right? So the QQ plot is very simple strategy to find out if your random variable is following this normal distribution or not, right? Or you can say Gaussian distribution or not, right? So what we will do, uh, we will take our random variable, whatever the data we have, 1,000 value or 10,000 value, anything. We will calculate percentiles, right? What we will do, we will calculate the percentiles, correct? And after calculating the percentile, you will get some values, right? Then I will then compare it with the. I can see theoretically I can take the normal distribution, right? Using the formula for value of x, I can generate a normal distribution. That's what we do in numpy, right? Numpy rand and like that, rand and random normal, right? So you can generate the random normal distribution, random data of normally distributed values. Now what I'll do, I will take again percentiles of this theoretical normal data. That's for sure, like it is normally distributed, perfect, right? Then what I'll do, I will now take a graph between this theoretical percentile, which is exact this line, right? This line, this red line, and I will plot my ordered value, or you can say the percentile values of my random variable, that is y versus x graph. And if it is falling on same line, that means my random variable is also following my this normal distribution as well, right? Or you can say Gaussian distribution as well, right? And if it is not following, I guess this graph is following exponential distribution or Poisson distribution. And if you take the percentiles, then it won't be following, it won't match with this red line. Red line is nothing but the theoretical percentiles of the normally distributed data, right? And see, by using this graph QQ plot, we are just comparing if it is fitting or not. Basically, if our random variable is following the normal distribution or not, right? So this is kind of a test, that QQ test, that we can use. This QQ plot can be used to identify if the distribution is following given normal distribution or not, right?
So Mayur,
Mm-hmm.
it's only for identifying whether the distribution is following normal distribution, or we can even identify other distributions with this.
Yes, we
I
can,
mean,
but there are some caveat. I guess we have something in Pareto also, that we can generate the theoretical Pareto distribution and compare them. But for
hmm.
large value of, I guess, lambda, or very small value of lambda, this will fail,
Okay, so you're
like
saying
that.
QQ plot will work only for
Good,
normal
like you
distributed
can
data.
say considerably very well for the normal distribution. But if you go with that kind of a thing, that which is very, you can say, crazy, exponential or Pareto like that, then it may fail. And see, it makes sense also. If let me give you a simple example. If you take the Pareto, right, and which Pareto you will take, basically that's the main question. Which Pareto you will take, with the, you can say, thinner tail or thicker tail, right? Both are Pareto with the different lambda, or even exponential. You can think for a moment. This time the QQ plot will fail, right? Which should I take to compare, right?
Okay.
In normal, it is really simple, right? Because on both side it is simple. If you even take the z value, or you can if even standardize it, then it will
Okay.
fall for the same value, right?
So you're saying it will work for normal because for them mu
Normal
and sigma is fixed.
considerably, yes. Correct,
Okay, and
correct.
for others, mu
Huh.
and sigma is not fixed. That's the reason it will not work for others.
Mm-hmm. And if you take, like, if this is the normal distribution that we have in our hand, And if I take some normal distribution like this, and if I want to compare it, then linearly it is increasing. See, right? There is some linear, you can say, kind of a relationship between the percentile value, right? It increases
Correct.
with it. But in case of this kind of a distribution, you can't have a baseline model to compare, basically,
Hmm.
right?
Okay.
That's why it will fail, like for those cases.
But theoretically, normally, I think I have read like you can compare any two distributions. It may not be normal. So we have taken normal, right? Theoretical. Maybe you can
Mm-hmm.
take uniform, other distributions as well.
Correct.
And also, you can compare two different distributions, right? Like here you are taking theoretical, but let's say you have two different distributions, and you
Ah,
want to know whether those two distributions
same
come
or not?
from the same
Yes.
distribution or not.
Hmm.
Then also you can use quick plots.
Correct. See, in this case, here I have, I guess this is a log normal. No, sorry, I guess this is a log normal or exponential, not a normal distribution. As this is uniform distribution, sorry. So if you take the uniform distribution and compare with this normal distribution, then definitely you will get something like this, right? So they are not following, they are not like on each other, right? They're not following the same distribution. And if you want to compare to distribution, then case test and that KL divergence is the better choice, right? Okay, with that in mind, let's jump on to the next, but really easy topic, or you can say we are using this most the standardization of data, right? And this is really useful to, and in you can say machine learning or real life example, because it is possible that all your data, or you can say parameter in a data set, are not following the same scale, right? If you have like height in a meter, like 0.8 to 2 meter, the range would be something like this, right? 0.8 to 2 meter like this. And if you're taking the weight in pound, then it will vary from 100 to 300, and I don't know if more than 300 also, right? And this can create a problem. I know that time I had no like a damn idea about machine learning model. That's why I've written something like this. While developing a ML model, one parameter will have more weightage over another. But now we know, like if you have this kind of a mismatch in scale, then it can heavily impact the distance, basically, right? So if the simple like small change in this height, if I change from 1 to 2 meter, it's just a 1 unit change. And if weight change 1 to 1 like 150 lb to 151 lb, there is not a big change, right? And but like intuitionally we know, like from 1 meter to 2 meter, it's a drastic change, kind of a double of a value. But for weight, it's kind of a 0.5% change, right? But if you measure the distance between two, both like both the point, then it would be similar, or it won't be like impacted much. That's why, to overcome this kind of a problem due to scale, we need to standardize all the data. So to make it all like following the same range, 0 to 1, right? So we are basically squeezing all the data given any range to 0 to 1, right? So standard normals, how to calculate the standard normal variate? That's nothing but it is denoted as z, or you can say z value. It is nothing but for give all the xi days we are calculating z, huh? It's not for whole data set. For each point we are doing this xi minus mu divided by sigma. So mu is mean, sigma is standard deviation, right? So this is z. Okay, and we will perform for all the value of xi to convert to that particular column, or you can say a feature, to standardize that feature, basically. Okay, now
But
it would be
this is the
following
property.
this.
Sorry, Mayur.
Mhm.
This is the this can be used with the normal distributed data. Now, other kind of distribution we can't use standard normal variate now because
Okay, huh. That makes sense, no? See,
hmm.
RV is following. Okay, yes, I forgot to mention. Huh? If you, that mostly like you, this can be used like in the normal distributed data. That's why we have one more thing called scaling, right? That normalization.
Okay,
That
okay.
that kind of a do a trick that scale all the data to 0 to 1. And but this is more like, I see, this is also useful in previously, when we had no like when we had this kind of a table to calculate the probability and everything. So what we do, given a value of xi, we just convert into g value. We know like what's the g value. If the mean is 0 and standard deviation or variance is 1, then using that z value we can go to the table and find out the probability value, right? And we can say that that's true for xi also, right? So this is more useful like in the normal distribution, and that what we are mostly using is standard scale, that 0 to 1, the scaling everything into like some same, you can say, scale. It is not always like 0 to 1, you can scale it to 0 to 5 also. Okay. Let's
Mayur,
see.
1 minute, Mayur. You spoke about the scale something. How we need to adjust that scale, like 0 to 1 or 0 to 5?
It's problem dependent, no, it is.
No.
Okay.
So what parameter we need to tune for that?
I don't get your question. Matlab, what parameter for? Like how to
See,
decide the scale that you are asking, 0 to 1 or 0 to 5 or 0 to 10, like
okay,
that?
so you're saying Z value over here is always
No, no,
0
no,
to
no,
1.
no. This is standardization of, you can say, normal distribution. See, if you're see, even for random variable, you are having mu and sigma square. So mean can be 20 and sigma can be 100, like that. But when you standardize the data, it would be following that x days would be following mean equal to 0, and standard deviation
1.
or variance would be 1.
Correct. And
So
you spoke about 0 to 5 something, na?
it's scaling, that
Okay,
normalization of
okay,
the
okay,
data, or
okay.
you
Sorry,
can say
sorry. I think
uh,
I got mixed.
min max
So,
scalar, I guess it is called.
Mayur,
So
so
that's what.
you mean to say, suppose there is a data set where we have height, weight, age, just
Hmm.
for example.
Hmm.
So for each column, for each
Uh,
feature, we will be doing this, right?
for each feature,
Yes.
yes, 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 then and only it
For each
makes
feature,
sense, no?
yeah, yeah. So that each feature is in the same scale. Then,
Correct,
Yeah.
correct.
So if the features are not in the same scale, if you
yeah,
use some of the machine learning algorithms which internally depends upon distance,
yeah,
those will get affected. Like decision trees and random forest, it doesn't matter whether you do scaling or not, because internally there is no concept of distance over there, right? But
yeah.
if you use KNN or SVM, which internally uses distance, those will give bad results.
Okay, yeah, got it.
So we had this
And
question
this,
in the exam, I remember.
I have this question. We can apply standardization to any distribution.
Yeah. I don't think it should be normal. I think you can apply anything, any distribution, but at last everything will be like a mean zero and a variation of one.
Okay.
All the
It
features.
means it means at last it will be normally distributed because it is
Yeah, all the
ultimately the normal
features.
distribution. No?
Yeah, all the here I think what's happening is two things happening. One, you are getting all the scales common across all the features, and
Mhm.
also it's being normally distributed because internally all the algorithms now want data to be distributed normally, right? So that's also happening here. Both things are happening.
Okay. Yes.
So will
Yes.
it
So you are
work with
also
Pareto
converting the data
also?
to normal distribution, transforming the data.
Yeah.
Hmm.
Mm-hmm. Okay. That's good. Actually, I had that doubt. Okay. Thanks, Viriteja. Yes. And it makes sense also, right? Because we are calculating this difference from the mean, right? So how it is deviating with the mean, and then we are dividing by deviation. Yes. So we can convert like any damn data into normal. Correct. Correct. I had that like wrong understanding. Okay. Let's jump on to next topic, which is nothing but the Kde plot, or you can say kernel density estimation, right? Estimators. So mostly we would be having a discrete data. The you can say the characteristics of random variable can be continuous. That height of data or time taken by a user on internet. It is. You can say continuous random variable, but in reality you want to be getting a continuous data, right? All the data basically on the number line. So what we are doing is we have this kind of a data. So this is the data. If you see this black spots, so it's nothing but the data point. So I have x equal to something near to 2.5, then minus 1, minus 0.5 like this, 2, 5, 6 like this, right? So what now I have created this histogram. Now it's clear, minus 5 to minus 4. I have just one value, so I just draw this much of a, and say this is not a pure histogram. I have divided by the total value like that. So this is the density function. So you can consider this as a PDF. So PDF, PMF, not PDF, PMF basically, right? So what I have done is I just created this kind of a PDF out of the discrete data I have. Now I want to estimate the smooth curve, right? This is the data all I have in my hand, just 6 observation. Out of the 6 observation, I want to create a smooth PDF, because PDF cannot be discrete. It's PMF who is discrete. So what I will do, I will create, just a second. Geyser बंद करो, उनको 0 लगा. Okay. So the how this kernel density estimation works is, we will take the kernels, and what I'll do, what we will do, we will draw the kernels around this data point, all the data point. So if I have this data point here, I will draw one kernel. Second data point, I will draw second kernel, right? And after drawing all the kernels for each data point, then what I'll do, the next step is to calculate the total distance, right? So just a second, copy image, I want to draw it basically. So after taking all these kernels, so eight this, I draw this one kernel. The second, third, fourth, six kernels I have. Now how can I estimate it? So I will start from zero. I will go like at each step, and I will calculate the distance, one plus two plus three. All this distance, right? Distance one, two, and three. Whatever the answer I get, it's nothing but my PDF value at that point, right? So again, if I take the example at this point, x equal to some value here, I don't have the data point here, right? I'm using the kernels to estimate it, right? So I will take this height plus this height plus this height. So I will get some answer, right? So this is the PDF of it. So I will start from zero up to the whatever the maximum value I have, or I can start at minus for something, the lowest value I have from the kernels. Then I will go along with up to the maximum value, and I will get this kind of a PDF. Yeah, so this is a really, you can say, good estimation if I try to draw it here, right, like this. So we have estimated this kind of you can say trend, or you can say a pattern, or how it will look if it so we are trying to mimic, like if it was a continuous data. We don't have data for this, right? But somehow we want to predict it. So what we have done is, and see, this makes sense also, right? Around this value I have more number of data points, right, occurring. So higher the density I have, right? So chance of getting new observation around this area is higher, right? So probability is higher because density is higher. Similarly, it drop a bit here, so it also drop a bit because I don't have any data. Then again it rise because I have two consecutive you can say observation like this. So we are basically trying to predict this kind of a smooth PDF out of a given this discrete data, right? And how to decide, like how to choose the kernel, right? I can take kernel something looking like this. I was trying to draw there, right, like this, or I can take big kernel or small kernels like this. And how many number of kernel you want, right? So basically the number of kernels is mostly fixed based on the data, how much data point you have, you put a kernel. But this thing is decided by one parameter of kernel. It is, I guess, called this thing, that h value, just a second, I forgot, bandwidth, right? So this bandwidth is calculated with trial and error mostly, and mostly it is the domain knowledge is mostly used, right? It is useful to decide, like what should be the bandwidth of h, or you can say, so no, sorry, bandwidth h should be for a kernel, right? And this example is actually explaining that. the true, you can say, density is this line, this gray line. If it is visible, I'm not sure. Let me have it here. This gray line is the true estimation, right? This gray line, right? And if I choose the different, you can say, kernels or different bandwidth for a kernel, I get different observation, right? Different, you can say, estimation. So for this green line, the bandwidth is higher. I guess it is 2. Yes. So if I take bandwidth of 2, then what's happening is I am taking big kernels like this, right? That's why it is giving something like this, right? So this is not a true estimation, you can say. If I take very small kernels like this, so it will overestimate. It is kind of a overfitting and underfitting, if you think intuitively, right? So I am now overfitting for each data. Say this is blues are nothing but the data point, right? So if I take this blue point, it is increasing, then again decreasing, for again one more blue point, it is increasing, decreasing like this. Yeah, so this is more sensitive kernel, this red is, and the h value should be very much small, right? Because I am taking this small kernels, correct? So it is not, you can say, fitting well this data, right? And this is true one, this is true one. So if I take h equal to some value 0.337 like this, then I get this black line. So this black line is a good, you can say, estimation of this gray line, right? So this is chosen using some domain knowledge, try and error, like that, right? So you can't have the perfect match every time. So there is no silver bullet that h equal to zero point 0.5 and it will work for all. No, it's not like that. We need to choose it wisely, right? So if you take very small kernel, it will overfit, kind of overfit the data. If you take very large bandwidth for a kernel, it will kind of underfit this data, this light green color. And with the perfect, you can say, kernel bandwidth, you can have the right, you can say, estimation of the data, right? So there is one parameter in the kd that's called the bandwidth. And I guess there was a really good discussion in group. There are so many techniques, 2 or 3 techniques are used inside the library to decide on the bandwidth parameter. We don't need to carry very much about it. There are like 2, or I guess maximum 2 or 3, right? 2 or 3 techniques which are internally used in the scikit-learn library to decide on this bandwidth parameter. Okay. Okay, now last thing, and you can follow this story, that you need to notice your data if it's normally distributed or not. Right now we know like what kind of distribution your data is following. Let's take for example Pareto or power law distribution. How can you normalize it, right? So yesterday we saw this. There is a problem here also. Here it should be xi. The formula is faulty here. Yeah, so here should be xi. So given a Pareto distribution or power law distribution, to convert it into normal distribution, we use the box-Cox transformation, and this box-Cox transformation will do all the mathematics on a given random variable x on this data, and it will give you some parameter called lambda. And this lambda is very much useful. And if it is log normally distributed that we yesterday discussed, I guess Giri pointed it, that if it is log normally distributed, you will get lambda equal to 0, right? So if it is log normally distributed, then it's clear, right? If it is log normal, then just take the log of all the data and it would be normally distributed. That's the definition of log normal distribution, right? So if lambda equal to 0, then you better know like this is log normal distribution. Just take this ln of xi, right? Not lambda, ln of xi, all the data. Just take the natural logarithm of all the data and it would be converted to normal distribution y, right? If it is not, then it will give you some value of lambda. And if you put the value of lambda in this equation, xi to the power lambda minus 1 divided by lambda, it will, the all the yi you will get for each xi, that this random variable y would be normally distributed. So this is the technique to convert your power law distributed data, Pareto distribution, into normal distribution, right? Okay, I guess the first chapter is over. Let's jump on to the next one. Now it would be really, you can say, interesting and easy at the same time. The first one is nothing but the estimating. The chapter name is nothing but estimating different parameter and confidence interval for like your estimation, right? So the first and the beautiful, or you can say heart theorem for statistics is CLT, central limit theorem. So what it states is, given any random distribution. So this is not looking like some kind of distribution, right? This thing. So given any random distribution, what it states is, whatever the data it is, you can take, okay, how why it is behaving like this.
Is it me only, or everyone is having issues with the sound?
Hello.
No, I think voice is fine.
Okay.
No, Mayur, I can hear you properly. Yeah.
Okay, I just removed this headphone. Okay. So the thing, the CLT, what CLT states is, given any distribution of a data, what I am doing is I will take the samples, right? And the sample size can be 30, 40, 50. At least it should be 30. So if you take the samples out of a data from the population of any distribution, and I just took a sample, right? Sample of size n. Let's say I just took 30 samples out of this population. Now what I'll do, I will calculate x bar of my sample, right? So x bar, that is nothing but the mean value. So I will put mean value, whatever the value I get at the x bar line, correct? Now again I will take some sample, I will calculate mean, I will note it, right? So again I will take sample, I will perform this operation as many time possible, right? As many time as it is possible, right? So like more the number of sample you take, uh, and basically it should be size 30, at least size 30, uh, the better your estimation would be, right? So the main core of CLT is, if you take this kind of a random sample and calculate the mean, right? We are noting a mean, huh? We are not noting this sample. So we are not we just note down all the mean values of the sample, random samples. Then this value would be following the Gaussian distribution, right? And this Gaussian distribution, if you take the mean of this thing, the mu, it is as similar as population mean, right? Any random data, given any random data, you want to calculate the mu, just take like sufficient number of samples of you can say good size, 30 or more, then you can directly calculate the mean, population mean, using CLT, right? Just take the mean of all the samples and take again mean of given data, sample means, right? I will use word sample means. And what would be the standard deviation of this Gaussian distribution,
Mayur,
right? Yes.
can you please, with any example, like if suppose population is 100 and then, kind of that example, can you just give?
Anything, you just give me all any random, or you can say garbage data.
Suppose the population is say 1,000, right? And
Huh?
in every sample, if we take say 100
Huh?
values, so
Yeah,
how would it?
definitely we can take that.
Yeah, yeah, please.
Still it will work, there is no doubt in it.
Yeah, so let's say there are 1,000 points in a sample, right? I mean, not
Hmm.
sample, the whole population. So, like you can take more than 30 points, and let's say you have done that repeatedly, like 10 times. Okay. So now for every sample of 30 points that you have taken, if you compute the average of those values will follow normal distribution, no matter what might be the population distribution might be.
Even you take it, you can take Pareto also, of any kind, like any crazy Pareto distribution, and if you apply CLT, you can find out the mu and sigma, right,
Okay, I think
of the
the
distribution.
question I think comes to our mind should be like, why are we doing this? Because as we know, usually all the data usually in the world follows normal distribution mostly, and also all the algorithms works mostly on good on normal distribution. So I think if you have a different population of different distribution, if you want to convert into normal, then I think you can also use this technique, and this
So is
works.
this a kind of a hack?
Yeah, hack where
Is
it's
this a kind of a
saying,
hack that convert any distribution into normal distribution?
yeah, any distribution to normal distribution, and they are also proved that the mean of the transform distribution is equal to the mean, will be very closely equal to the population mean. And that depends upon, like, usually the samples that you have taken, the number of samples, usually that depends upon number of samples that you have taken, and in each sample how many points you have taken. So I think basically they're saying at least there should be minimum 30 points for each sample, and I think it will be good as many samples if you take and do the math.
Hmm.
Okay,
And
so
we
any
will.
distribution means even the discrete random variables, for them also it will work.
Any guys.
Any distribution, Pareto law, no,
Or even also
exponential, anything,
this
any
also,
distribution,
even
any random distribution,
three
even if
mountain
you don't
also.
know what the distribution also,
Hmm.
at the end everything will convert to normal.
And you're like asking a question, just say why we are actually calculating or why we are finding using this CLT theorem. So what would be the reason for that? Because if we have 1,000 data point as a population,
Hmm.
and we can easily take the mean. So just simply write mean function. Let's say mean is 200 or maybe 300. So why we are converting it into the Gaussian and then we are taking the mean?
So I think one that I already said, that all the algorithms, all the machine learning algorithms will mostly work on normally distributed data, right? So
Mhm.
that's one thing. And another thing is that if let's say you have 1 lakh points,
Yes.
population points, instead of calculating mean of those, I think in initial days I think this is the problem. You may not go through all the 1 lakh points and you may not calculate the mean. So idea that they came up with is like, okay, it's taking a too much process, can we somehow, is there any hack to it? Then I think they came up with this technique. Okay, you don't need to go through the no 1 lakh points to calculate the mean. Just take some samples out of those, repeat those samples for multiple times, like 10 to 20 times, and just take the mean. And then they proved that those mean and the actual population mean will be very similar. So that's one, I think, why they thought of this
Yeah.
technique. So instead of
Okay.
going through
Also,
all 1 lakh data points and calculating the mean, now they can just have some 1,000 or 2,000 points, and the mean, and it's equal to the population, right?
yeah, also this normal distribution is extensively studied. So we try to convert every distribution to normal so that we can also analyze the data properly. Like we have 68, 68, 95 rule. Like we
Hmm.
can, so we can apply many things of normal distribution and analyze the data properly, because there are thousands of distributions that we don't know. So converting them into one distribution helps us a lot with analyzing.
Okay, sounds good. So this is the one of the major reason why we use CLT
Yeah,
to
because we
convert into
can,
normal, and
yeah, we can
normal
use the
is
properties of Gaussian distribution and analyze
right.
it.
Sounds good. Thanks.
And see, like sometimes like it is not even take even to like you need to don't know all the value of population also, right? Just go out, take the 1,000 sample of 30 each, and you can directly give the answer what is the mu, like, and it is very close, right? I was just trying to open this thing, but I don't know why it is taking so much of time. First time I'm running basically VS Code on this system, so I had created this thing that you can take like any kind of a distribution, and it will be able to find out the mu and sigma basically, and these two are very, you can say, useful parameter, right? That you want to calculate on your population data, that what is the mean of a data and what is the n, or sorry, sigma of a data, right? So just go there, just take 30,000 sample, and using the CLT, you can directly say like this is the mean and this is the sigma, and it would be really accurate, correct? Okay. So the whatever the mean we have here is equal to sigma divided by root n. So this is the like most confusing part that can happen in case of numericals. So sigma divided by root n is nothing but sigma, you can say s, right? So the standard deviation which this Gaussian you can distribution is following here, right? So it's equal to sigma divided by root 10. So whatever the answer you get, let's say you get 30, just multiplied by root 10, right? So your n can be 1000 or anything, how much sample you took, right? So that will be you can say estimation of your population distribution. So this sigma is population distribution which is unknown, right? So this sigma population distribution we want to know, it is equal to sigma sample multiplied by root 10, right? Here I have written root 10 multiplied by sampling mean standard deviation. Okay. And this is kind of a rule of a thumb that they have observed. There should be some proof or cannot be. I am not sure. But if like n is greater or equal to 30, CLT works like beautifully. And more the number of sample, more the better. It's the always golden rule. Correct. Yes, this is a really good video. That guy in this video has taken like all sorts of you can say distribution, power law, exponential, uniform, all sorts of distribution and try to apply CLT. After like 100 or 200, max 300 iteration, you would be able to like predict the like mu or you can say mean value and standard deviation very closely applying the CLT, right? Let's.
Mayur, only one thing.
Mhm.
One thing I need to ask. That part, please, can you go to that page? The second point where you have explained the standard normal, standard deviation, that is something sigma multiplied by root n. But in the formula, we have written sigma upon root n. So I didn't understand that multiplication.
Array,
In the
okay, okay,
okay,
okay.
go below, go below.
This thing, no, that's what I tell you.
Just
Array, okay,
this
yes,
this
yes, yes,
this
yes,
one.
yes, 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 yes. I guess yes. There is a like really big mistake. Sampling means standard deviation. No, no, yeah. You got me actually. See, this sigma divided by root n. So let's say I
Hmm.
applied this CLT on this data, right? And I got
Hmm.
after taking all this thing, all the mean value, I got some Gaussian distribution whose mean is similar as population distribution, right?
Hmm.
But there would
Okay.
be some standard deviation of this Gaussian distribution, 30,
Hmm.
40, or 50, let's say 50. So
Hmm.
that 50 value, 50 is equal to sigma divided by root 10. And what is this sigma? Sigma is nothing but population
Okay.
distribution,
Okay. Okay.
right?
Okay. Okay. Okay.
So this
Got
sigma,
it. Got
as
it.
we know, that sample distribution, this the not the standard deviation of the sampling distribution, we know, right? That I will multiply
Hmm.
by root 10, then I will get the value of sigma. And what is sigma? Sigma is population distribution. See here, I have written this
Okay.
sigma here, right? That's why this formula,
I
population
got
standard
now. I
deviation is
got it
equal
now.
to root 10 into this. That's why I told you,
Hmm.
like, this is the most confusing part when calculating the numericals. Okay, so don't divide the sampling distribution by root and multiply it. Okay, next thing,
N is sample size or
n
actual
is
data
number of
size?
samples we are taking. Sample
Okay.
size, yes. How many samples we are taking, and sample size is n or 30, right? So this is m, or you can say how many number of samples we are taking, and n is 30. N is sample size. This n in the formula, correct? If it runs today, then this would be really useful to see. No module name matplotlib. Okay, leave it. Mm, okay, you have the sample and you want to estimate it some parameter. Okay, what's the next topic? Uh, this CI. Okay. Uh, just a second. Okay, now the next topic is this confidence interval, right? So, like every time it is not possible that you predict the exit mu, right? And it's it makes sense, right? That you say like population mean is 60. No, if you say it's between 55 to 65, right? With this 95% confidence or 90% confidence that this is the range that your mu would be, then it makes sense because you don't have the whole population data. Then how can you be like sure that it is 55 only, right? So how can you give this kind of a range and with some confidence? That's the next you can say our quest. So let's see. So there, I have taken some case. The first case is the normal, the distribution is normal, right, or Gaussian. This is the, you can say, simple case. Why? Because if it is a Gaussian or normally distributed, then we know like all the value of mu, sorry, not mu, all the value of random variable, it would be in the 2 sigma range. And what is the 2 sigma range? Mu plus 2 sigma, mu minus 2 sigma. So between this range, all my data would be there, and mu would be only be there, right? Mu would be there only because my 95% of data lies between mu minus 2 sigma to mu plus 2 sigma. So it is 95% chance that mu lies in this range, mu minus 2 sigma, mu plus 2 sigma, 150 minus something, 150 plus something, right? I'm just taking some random example. So it is if it is normal distribution, then our life is simple, right? Now, and see, okay, to find the confidence interval for 90%, we just take the corresponding value in that Z table, or we can calculate using that crazy looking formula 1 divided by sigma root 2 pi e to the power something like that, right? Okay, let's go to the next topic, that CI for a mean of random variable. So our task is to calculate the mu, or you can say, what is mu? That mean value or average value, and confidence interval around it for random variable. So let's there are two cases basically. The case one is that population standard deviation is known, right? So whatever the population that we are trying to study, we know like what is the standard deviation. In that case, life is simple, right? Just take the sample. Now we will apply this CLT, right? That we just discussed actually, right? So this CLT we can use for on the population. Just take the sample size of 30, take a large number of samples, 1000, 2000, 3000, how much money you have. Then what I'll do, given the sample, I will have mu, right? That population mean would be nearly equal to sampling mean, x bar, right? Now but this is not the, you can't say like this is equal to this, nearly equal to this. So I need to give some range, right? Some room for error, right? So if I get 55 here, I need to say like from 50 to 60, I am 90% sure, 60% sure, like that. So how to arrive at that point? Now the population standard deviation is known, right? The case is population standard deviation sigma we know. Now what I'll do, we know this sigma, right? And now what I'll do to give this kind of a limit that my mu belongs to, or my this mu, or you can say population mean belongs to this range x bar minus 2 sigma dash x bar plus 2 sigma dash. X bar is nothing but whatever the mean we have calculated from sample, right? This mu is a variable, huh? We don't know what is that. Our task is to find that, or in other word, to be precise, our task is to find this thing and this range basically, right? So this x bar is known, minus 2 sigma dash plus 2 sigma dash. 2 sigma dash I am giving, so that's nothing but and this is following normal distribution, right? After applying the CLT, so I can use this 68, 95, 99 rule. So according to 68, 95, 99 rule, the 2 sigma range will get all the data, 95% of data, right? So my mu would be definitely there, 95, with that 95% of a chance, right? Now what the hell this sigma dash is? Sigma dash is nothing but what we have seen, sigma divided by root n, right? Sample standard deviation is equal to sigma divided by root n, correct? And that we saw actually. So this is nothing but my you can say this estimation of mu in this range, right? And why it is exact opposite? Because this is the estimation for this thing, you can say population, and the sigma which we know is nothing but samplings, and so that's why we are dividing by root n. And still I'm finding the answer why we are not multiplying and dividing. But still, like, I'm not able to understand, because as per my logic, even I was discussing with this Vinit, it should be sigma should be equal to sigma dash into root n, but why we are dividing it here, I don't know, like what's the logic behind it. I check out some website or something, but everywhere they have taken this kind of a thing. Does anyone know the answer? Why we are taking this sigma dash equal to sigma divided by root n?
Is it
Any
because that this is we are calculating sample standard deviation? I mean, this mu is for sample, and the above one was for population. Is that the case?
this sigma is for population, right?
Yeah,
Okay, yeah, yeah, it's now it clicked. See, this is already known now. Sample standard deviation. We just
correct,
applied the CLT, right? Now we know the
correct.
distribution. So
Yeah,
this sigma dash is known, and the formula just we are putting basically sigma divided by root n, right?
yes,
So
yeah.
here we had the answer. Yes, 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 yes. Okay, euphoria moment for me. Okay, eureka, not euphoria. Okay. Let's take the case which is more realistic, that population standard deviation is unknown. Right? We don't know like what's the standard deviation, what's the mean. Now you want to calculate the mean. Now what you do is um, we apply the student state distribution to estimate the population standard deviation. Right? And this state distribution is the very simple idea, but magically it works really well. That to calculate this thing out of the sample, if you take the sample size of let's say 1,000, right? Just take one sample, right? You just take one sample. Now uh, what I will do, I will calculate the population standard deviation as sigma divided by n minus 1, that variance divided by n minus 1. I won't take n, I will take one value less than n, n minus 1. It's all idea behind t distribution, and it works magically. I had shared that video also on the Khan Academy. There was one competition also, that every like everyone created some kind of a you can say animation or working, you can say demo, that you can enter the data and simulate that if you take n minus 1, then it will basically converge to like it will be the best estimation for the population mean. They try to calculate for n minus 1, n minus 2, n plus 1, n minus 3, like that, but every time n minus 1 gave you the like perfect, you can say, estimation of the population mean. If you use this if you use in variance formula, instead of n, you just need to use n minus 1, use n minus 1, right? And I guess there is a proof, but it was beyond my mind and beyond the scope of our course basically, right? So if the population standard deviation is unknown, just take this variance equal to the variance, sample variance, while calculating estimating the population variance. Just take the n minus 1, not n, right? Okay, it's around 10:40.
Yeah, so basically, all these techniques are extensively used in polls prediction. Even Prashant Kishore's team, everyone, right? They use these techniques because
Prashant
let's
Kishore.
say,
uh,
yeah, they have a team, right? IPAC, I guess, if I'm not wrong. So
okay,
it's a
okay.
political group. So they're, I think they use,
uh,
so what they do is, let's say Prashant Kishore will take, let's say Andhra Pradesh, Tamil Nadu. He will choose one party, DMK or ADMK. Before choosing that itself, he will let his people who is working for the IPAC, he will ask them to go to villages and towns, do the survey,
okay.
and based on that survey, he will decide to which party he has to support.
Okay.
He will get
That's
accurate,
interesting.
mostly accurate results. So in that case, let's say he won't go in a village. There were 1 lakh people,
Uh-huh.
so their employees may not go to those whole 1 lakh people and ask them like which one do you vote, right? For
Hmm.
which one do you vote? So maybe they will take a simple samples out of those.
Hmm.
They can maybe variety of data, and based on that they will come to a conclusion that okay, I think this is the party that has most probability. Maybe they also give the confidence interval, saying that maybe this is the
Okay.
confidence that this is the percentage of confidence that we are saying that you might get this many votes in this particular village or
Hmm.
in this particular constituency, something like that. Yeah, these techniques are
Great.
extensively used. I also read in a lot of blogs that all the poll strategists, everyone uses these techniques. I think that makes sense. You can't
Yes.
go through whole population, so you will take samples.
Hmm.
Based on that samples, you will estimate. But the crux part will be like what. the variety of samples that they look at.
Correct. More variety of sample you get, more
Mm.
accurate your result will be. Yes.
Mm.
And even I was thinking one day, I just promised that I won't go much in detail, but see, what I was thinking is we are taking this random sample, right? So you'll take some sample from here, you'll take sample some from here, some from here, some from here, right? So basically you are this is kind of a like bootstrapping. Basically CLT is nothing but a bootstrapping kind of a thing, correct? You can open the IP bin column instead. That's a good idea, but will this widget work? That IPY this work? That widgets will work, or I don't know. IPY widget. That's fine. I just wanted to saw this CLT demo, but that's fine. The thing is, this is the same computer that I use, but I logged in Windows due to this examination and everything. Okay. So where were we? The last topic we saw. Okay, the next thing that n minus one basically, and I just pasted a link. This there are like two or three demos that Khan Academy is having. One, two, three, I guess yes. Two or three demos are there that they actually conducted this kind of a simulation on random data. What happened if you take n minus one, n and n plus one, which is the best estimation of a population mean, right? And they prove it using this kind of a bootstrapping method that n minus one works like every time. Okay. Having said that, let's jump on to the next thing that now you still want to give this kind of a confidence interval, but it is not normally distributed, right? The data is not normally distribution. A distribution is looking something like this mountain like thing, right? And of Uttarakhand. Now, now you want to even I make mistake in this formula, so better to remember just one formula and derive rest of it. So what this Chebyshev's inequality is saying, given any random distribution, the chance, or you can say the probability of finding your data, right, or you can say the mean basically, is this to find the mean or this thing, the probability. Why I'm making mistake now?
Confidence interval, no?
No, I think
Uh,
Chebyshev inequality, right? It's like no, for the normal distribution, like you can say 95% of the data belongs to this
Correct.
mu to this
Hmm.
sigma.
Hmm.
But for let's say for other distributions, how do you say that?
How do you say that? Yes, 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 yes.
You
So
can so that's why we use this
correct, correct.
inequality
So
to
this P is nothing but my probability value, right?
yeah,
Correct. So what's the probability that my x is lying between k sigma 2 plus k sigma range? So it is k sigma range, 1 sigma, 2 sigma, 3 sigma, any range, right?
yeah,
So if
yeah.
it is not normally distributed, we can apply this Chebyshev's inequality. And what it is saying is that my x lying between k sigma range is greater or equal to 1 minus 1 by k square. So this is the original formula, and we can derive it. We can derive this formula, right? So the chances, or you can say the probability, the all my data is distributed between this range, k sigma range. If you put k equal to 2, right, that's nothing but x is lying between 2 sigma range, mu minus 2 sigma and mu plus 2 sigma. In normal distribution, we can directly answer it's 95%. 1 sigma 68, 3 sigma 99.7, right? But what about other distribution? So we can apply this Chebyshev's inequality, and we can find out that in between this range, right? So if my mu, this x lying between this range mu minus k sigma to mu plus k sigma is greater or equal to 1 minus 1 by k square, right? And after this, like less than mu minus k sigma and greater than mu plus k sigma, so it's nothing but x minus mu mod of x minus mu greater than k sigma is less or equal to 1 plus k square, right? And there was a simple numerical in mid-sem also that using the Chebyshev's inequality find out the interval, or you can say the probability of being x in the 2 sigma range. So k was given and we need to find out. 1 minus 1 by 4, like that. Okay. Now, third question that we have in our hand, that we have seen this kind of a method, or you can say these are all like old method, that the computation cost was very much high, right? We didn't had higher CPU, GPU, or anything. But today's, or you can say the most, you can say cool technique that we have is nothing but the bootstrapping, right? And you can rely on bootstrapping a much, because it is not using a damn any formula. It is not using any formula, any theory, or anything. It's just taking the random samples, or you can random samples out of your population, and then try to find out, like, more the sample, better it is, right? So it's kind of a CLT. But how it differs from CLT is, now let's say we want to predict, we just talk about mean and standard deviation and everything. But let's say we want to find out the median of a data, right? Population, how can you do that? So what I'll do using the bootstrapping is, and we can calculate everything. See, 90th percentile if you want to calculate, median you want to calculate, quartile you want to calculate, IQ or anything. So the data set we have in our hand is x1, x2, x3 up to xn. And now I am taking the sample, right? Sample Si now. And this sample size is nothing but m. So this sample size can be 30, 40, 50, 10, anything, right? And I am taking k equal to 1000 samples, right? S1, S2, S3, Sk, and each S1 or S2 is comprising of m values, right? So let's say 10,000 sample of size 20, like that. Now what I'll do, I have 10,000 sample in my hand. Now what I'll do, I will calculate, let's say I want to calculate median. So for each sample, I will calculate median and note it down, right? So I will get these 1000 medians for 1000 samples, M1 days, M2 days, M3 days, M 1000 days, right? Now, out of all this thing, I can definitely calculate 2.5 per, like percentile, or 97.5 percentile, right? So the confidence interval for 95%, that means I am taking from 2.5 to 97.5. So it's nothing but the range of 95%, right? From, right, 95%. So given this two value, so after from this 1000 value, if I have 1000 value, what would be my 2.5 percentile, right? It would be nothing but 25th term. If I sort it like in ascending order, my 25th term is nothing but my 2.5 percentile. And my 975th term, what I have got, it's my 97.5th percentile. So this is giving me my 95% confidence interval range for my median value. If it is, let's say, 2 and 10, so I can, like, with 95% confidence, I can say that my median is between 2 to 10. Correct? Any doubt, guys, now?
Can you come that up again, Mayur?
Sure. So given any population, right? What I'll do, I will take 1000 samples, 1, 2, 3, 4, right? Up to 1000 samples I have taken, right? Now, next step, what I'll do, let's say we want to calculate median value. So I will calculate median for this. It's M1. Median for this is M2, like this, M1000, right? This would be in not ascending order. Now I will order them, like, I will put them in the ascending order. M1 dash, M2 dash, up to M1000 dash, right? So this is in ascending order, right? Now if I want to say, like, in 90% 95% confidence interval, if I want to give for my median value, I will take the 2.5 percentile out of this data, and 97.5 percentile, right? So it is nothing but the 95% if you think intuitively, right? 2.5 to 97.5, it's nothing but 95%. I am just not ignoring just this 2.5% data here and 2.5% data here.
Ah, now I got it.
Correct? So
Hmm.
whatever the value I have here, let's say 2, here let's say I have 10. So I have this 95% confidence interval, that 2 to 10. That means my median value would be between 2 to 10 with the 95% of a chance. Correct? and I have that simulation also for confidence interval, but it won't run on this PC because I am missing so many libraries. I will try to run it on Colab if you're interested at the end of a session, right?
Okay.
Mayur,
uh,
hello.
हाँ बोलो बोलो.
I done in bootstrapping. I was really confused at the time, but the point I got, which whenever we have given a population distribution, the data is too much, so we have done the
Hmm.
bootstrapping and we have calculated 95 percentile by the method which you have explained. Okay.
uh,
So does it mean that we are saying that whenever we will calculate the standard, sorry, the mean or whatever we have calculated, whatever the parameter we have calculated
hmm,
with the help of bootstrapping method,
hmm.
and if we have calculated the 95% confidence interval, it means that if we will calculate the same parameter with any other method taking the whole population distribution into consideration, 95% of the times the data sorry, the median or whatever we have calculated will lie between that range.
Correct.
That is the mean, na? Actually,
Hmm.
okay,
So
that is the actual meaning, na?
uh,
Because sir was saying, or somewhere it was confusion in the comments also, that like saying it is a 95 we have there is a 95% probability, so it's a wrong thing to say. Sir was saying that in the video in the CLT, I think, or in bootstrapping somewhere he has explained it like that.
okay,
So I was
so
confused,
what's
then
the
I have
meaning of this
concluded this.
95%?
That is about the p-value.
Okay.
That
Must have.
I think I remember saying that. I remember even Shrikant sir was saying this, but I think it was for the p-value.
Okay.
Okay.
Even I am confused. That's why I'm asking, like, what this 95%? See,
No,
even
no, but
the word
whatever
is
we have done now,
confidence. No.
whatever we have done now, whatever we have done, according to that, I have understood that why when we say that we are 95% confident, it means that whenever we will calculate the whatever parameter we have calculated with
Hmm.
the any other method,
Hmm.
taking the whole population distribution,
Hmm.
it will be like that. If we have, suppose we have calculated 100 times, then 95 times the median, the value of that particular parameter which we have calculated, will lie between that confidence interval which we have calculated with the using the bootstrapping technique.
Okay. So if we perform this
That is
something.
the interval.
Okay.
Because as we can see now, like 20, for 1 to 2.5 percentile we are not taking, and they are 97.5 to 100 we are not taking. So we are excluding 2.5 here and 2.5 there.
Huh.
So there are 5% points. Maybe there may be 5% points which may not lie in our interval. What we have calculated using the 95th percentile technique.
Okay. Okay. And that's nothing but the probability, right? That 95%, it's for
Exactly, but
90,
sir,
100,
sir
95
had
out of
mentioned,
100.
that's why I was confused. Same, yeah, yes,
Huh.
because every time we are getting the 95%.
Hmm. So 95 out of 100 will work. Okay. So correct, correct. Okay, that's correct. Let's. Okay, what's the next topic? Any more doubt or any inputs, guys? Because this is interesting. Yes. Uh, okay. Last topic of a day: finding the relationship between two features. And under this, we have four things to cover: case tests, that covariance, SRCC, PCC, and SRCC. Okay, so now our task is to find out the relationship between two features, or you can say random variable, right? Now, as we have studied machine learning, now you can understand what features is, right? Features are. So, given two, you can say features or column of data, how can you compare? How can you find out the relationship between both, right? So, the first test is nothing but the case test, and case test is very useful, but we drop and we go with the Kale divergence just because this is not differentiable, right? So let's see what case test is. And case test is nothing but one kind of a hypothesis testing. Okay, so in case test, okay, I have like one topic I don't have notes is hypothesis testing. It was taken by Suman. very beautiful, you can say, ppt, and so many numericals he taught, right? So I, for hypothesis testing, I don't have any notes. Okay, so how what's the case test, and how what's the hypothesis testing that we are performing in case test is the first. What we will do is the null hypothesis is basically both are following the same distribution, right? And our statistics that case statistics that we are using in case Conglo Kolmogorov Merino test, right? It's nothing but the supremum value, or you can say the maximum value, or maximum difference between two cdfs, right? So this supremum function is nothing but taking this is not, see, f1 and f2, just don't concentrate on it. It's nothing but this supremum, it is saying the max, basically the max. So we will calculate the difference here wherever we get the maximum value, the value, that value is used as the statistic value, right? So it's kind of, you can say, mathematical way to present that what is the highest difference, or you can say the biggest gap between cdf, right? So this biggest gap that we can allow, it depends on the value of alpha, right? That alpha, and this thing, and using the alpha we calculate this c alpha, right? So this alpha, that level is called what is that alpha, what's that, guys? My mind is blank right now. That alpha, that limit that we decide, like if it goes beyond this, we will reject the null hypothesis, like that. What's that significance level? Okay, significance level alpha, right? So based on the significance level, this c alpha will vary. Okay, now let's jump onto the mathematics behind it. So we have this two distribution, x1 and x2. Our x1, we will say the cdf value with the capital f1. You remember that cdf is capital F, pdf is small f. So f1 is nothing but the cdf for this blue, or you can say this x1 distribution. F2 is nothing but the distribution of this F2 is distribution of this X2 data, and N and M are nothing but how much of data you have, basically the row count, right? So F1 NX and F2 NX, it's a cumulative probability. That's nothing but, say, cumulative, not probability. It should be cumulative CDF. So it's cumulative density, right? And density is like nothing but density, or that uh, density is made up of probability. Okay. Now this k statistic dnm, that is you can say deciding parameter to reject the null hypothesis. It's nothing but the maximum distance, or you can say supremum distance at x, and this x is nothing but this thing, zero point 0.5. At zero point 0.5, no, sorry, it is 1, right? 0 1 2. So at x, this at x, where this distance is maximum, f1 nx and f2 nx, the distance is maximum, right? Now the null hypothesis that we assume that x1 and x2 are same distribution is rejected at level alpha, right? This alpha we can take on our you can say this significance level is mostly domain specific, right? In hypothesis testing, whatever the alpha, like what alpha you should take in medical, it would be very less. In some other you can say not critical thing, you can take alpha very high also, 5%, 10%, like that. But if you don't know, you can take always alpha equal to 5%, right? So given the value of alpha, we just need to calculate the c alpha, right? Just to make look this formula very beautiful, they have just put the c alpha here, and they describe what is the value of c alpha, right? So this is the formula to calculate the c alpha given the value of alpha, ln alpha by 2 into 1 by 2, or this thing. And if you put this here and take the multiplication, you get this thing, right? So this formula is not looking good, so that's why they just put c alpha here and calculate the c alpha outside this formula, right? So as you can observe, right, like smaller the value of alpha you take, just 0.1% or 0.1%, the C alpha value is very very high, or comparatively high, 1.9 here. So if you take 5%, it is 1.3. If you take 20%, it's just 1.07, right? So what is the meaning of larger C alpha? Larger C alpha, so larger the C alpha, larger this value would be under root nm divided by n plus m divided by under root nm. So if this value is very very high, my dnm can be high also. I am allowing like large gap between two distribution, right? If I don't care, like they can have like if I don't care much, and if I don't care much if they like both are you can say exact same distribution or not, I can take the larger value of alpha. That is allowing larger value of d basically. And what is d? D is nothing but the largest gap between two cdf, right? And if I am very conscious, and if I want both the distributions should be overlapping each other kind of a thing, right, or same distribution if I want, then what I'll do, I will take the smaller value of alpha. If I take just 1%, right, then the C alpha is higher, 1.6. 1.6. I guess I messed up. I just explain like in other way. Smaller this value, we have this greater than sign. So if d is greater than this, then we will reject the hypothesis, right? So smaller the value, larger, like smaller the value of d, you will allow. So how it's working now? Okay guys, so let's not get into it, but this is the formula that we need to understand. And there can be a numerical on it, correct? And alpha is nothing but to decide like how much allowance you want to give, correct? uh, okay, in C alpha we have this minus value, then how it is not directly proportional to alpha? Okay, let's take the next topic because it's 11 already. I will try to explain like why this C alpha is smaller and why we are allowing this D smaller. Let's not get into it, otherwise it would be 11:30. uh, Last three topic of a day very like very similar to each other. That's nothing but to calculate what's the relationship between two random variable. Are they like having a linear relationship or not? Are they having any kind of a monotonically increasing relationship or not? How to decide on that, right? So the first and very simple approach that they have taken is nothing but the covariance, right? And covariance is nothing but xi minus mu, yi minus mu. And if you go into detail, if it is having this linear relationship, the covariance value would be positive, right? Covariance value would be positive in this case, right? If there is a, if x is increasing and along with if y is increasing, as x increase y increase, then it's nothing but the direct proportionality between x and y. X is proportional to y, then the covariance value would be positive. In other case, if having negative, or you can say inverse proportionality, that x increase but y decrease, then the covariance value would be less than 0, or it would be negative basically, right? And this is the formula. Okay. And the covariance between same variable x and x, if you take, then it's nothing but xi minus mu x, xi minus mu x. So it's nothing but if you observe, this is nothing but the formula of variance only, 1 by n xi minus mu x square. So this is the variance basically, right? Next, PCC, Pearson correlation coefficient. And why it is useful is, there is a problem in covariance that it depends on the scale. Why it depends on scale? Because we are taking xi and mu, right? We are not taking standard deviation in picture, right? So if I just change the scale, if let's say my xi value in height was first in pound and I then convert into kilogram, right, then covariance value will also change, though it would be positive or negative, but it will change, right, with the change of a scale. And this is not a good thing. So what So the thing is the Pearson correlation coefficient is nothing but just take the correlation covariance and divide by this thing, standard deviation, right? So if you divide by standard deviation, then what will happen is, given like any scale of a data, if you just change the scale of a data, then this whatever the coefficient you get for PCC, Pearson correlation coefficient, would be similar. It is independent of scale, right? So it's just a slight, you can say, modification of covariance between x and y, right? And here we have this kind of a example, and from this, I guess there this was also there in exam. They just made the question out of it. So if it is having a linear relationship like this, right, no spread, right, this is a straight line, and if the slope is positive like this, x and y are in a positive, or directly proportional, then you will get the positive value, right? Because covariance would be positive. If it is like this, if it is decreasing or inversely proportional, x is increasing, y is decreasing, you will get the negative value, right? If it is spreaded like this, then the Pearson correlation coefficient will decrease. Here I had 1. If it is a spread of a data like this, 0.8, there is a more spread, 0.4. And if it is this kind of a circle, you can't draw a line, right? This is not looking like a linear data. Then it would be 0. But it is not able to get this kind of obvious relationship, right? If it is quadratically increasing monotonically or like that, quadratic relationship is not calculated by Pearson correlation coefficient, right? PCC. So that is solved by our next coefficient. That's nothing but Spearman rank correlation coefficient.
Just
Okay.
to add one point more, so
Just a
there
second,
is,
guys.
yeah, one important point between covariance and correlation is that in covariance it will only
Hello.
tell you whether two variables, like, there is a relationship between them, but it won't quantify it. Like, it won't tell you how much is the relationship.
Hmm.
But in the Pearson, it will tell you exactly whether it will
Hmm.
quantify the relationship, whether it is high, low, or zero.
Hmm. Correct. If it's exact, you can say straight line, then it's saying 100%. Yes, 100%, it's the linear data. But if it is a spread on this line like this,
Yeah,
then it's
here
pointed.
you can see like values like 1, 0.8, 0.2,
Huh.
and 0, something like that. So based on that, you can able to say,
Hmm.
know the quantifiable relationship between those. But in covariance, it won't tell you that. It will just greater than or less than, that's it.
Correct, correct. If it's directly proportional or not, right? Directly or inversely.
Yeah.
Correct. Let's take the last one, Spearman rank correlation, and the idea behind this is very, you can say, easy. So it should be like in 16th or 17th century, I believe. But what they have done is, just take the data, all right? Just take the data x and y, and what they are taking is just calculate the rank, right? So rgx and rgy are nothing but the rank variable of rv, the random variable x and y. So they are not taking the data, basically x and y, whatever the data I have in the x and y, I don't care. I will just give the rank, right? So what intuitively they are doing is, if I have two variable like this, 1, 2, 3, 4, 5, 6. Let's take some example like this: 11, 23, 12, 34, 45, and let's say 23 again, or 24. Now I have one more, you can say, random variable. It is going something like this: 101. Let's take smaller value: 0, 1. 1, 2, 3, 0, 2, 0, not 0, 2, 2, 3, 0, 4, 2. Basically, what I'm doing is 1, 2, 3, 4, 0, 4, 0, 5. Again, this should be 0, 2 array. Yeah, I messed up. Uh, let me change it. 0, 3, 2, 4, 5, 6, like this. So, if I ask you, like, if there is a relationship between these two data, then what we will do? We will see, like, what is the smaller value? Okay, 11. What is the smaller value here? Okay, 11 is tied to 0, 1. Cool. Then I will say, what's the next value? That's nothing but 12. It is tied to 2. So, it just increase 0 to 2. Then I go to, like, next 11, 12. Then I have 23. And I get 0, 4. Then 24, I get 0, 3, right? Here it should be 3 and 4 here, but let's say it's never perfect in real world. Then 34 and 35, then again it increase like 0, 5 and 0, 6, right? So now what I'll do, I will give some range, right? So I will take, not range, rank, sorry. So how to give the rank? So rank of 11 is nothing but 1, because it's first, the smallest value. So here the rank is 1, rank 2, rank 3, 4, 5 and 6. For this data, the rank would be 1, 2, 3, 4, whatever I have written, it's something like this, right? So, if the rank of a data is having a good, you can say, relationship, right? They say 1 and 1, 2 and 2, right? So, it is increasing, you can say, linearly. Apart from these two data, 0, 3 and 4 data, it is increasing like this. So if the rank of a data is having some linear relationship, or it can be quadratic also, right? This is not linear data, right? It can be quadratic also. For one I have 11, then two I have 12, then for three it directly jump onto 24 or 23, right? So if it is linear or not, if the data is you can say increasing in parallel, right, in you can see in order, then we can say there is some relationship between these two data, right? So just kick out all the data, just don't look at the data, just take the rank out of it and see if the rank are matching, right? That's the whole idea behind this thing, Spearman rank correlation coefficient, right? So it's rank correlation, not a data, right? So what we are doing is, we just take all the rank rgx and rgy are nothing but the rank variable for rvx and rvy that we just calculated 132 142 563. And now if you put this rank data, it would be something like this. There is some hiccup like this, and then again linear, right? 3 to 4, 4 to 3. That's why I draw this kind of some hiccup. Then again it would be linear, right? So based on the rank we are deciding if we are having this thing or not, correlation between x and y or not, right? So it's basically nothing but pcc. See this row we used for pcc, this row or delta, I don't know, I guess it is called row. So this is nothing but Pearson correlation coefficient between the rank variables of given random variable x and y. So rgx and rgy are nothing but the rank variable. So given the data, just give the rank, and between these two rank data, calculate the Pearson correlation coefficient (PCC).
So
That's
Mayur,
nothing but assertion. Yes.
formula is same between Pearson and Spearman. Just the values. Like in Pearson, we are using values, actual values, and we are ranking them, and we are using rank in Spearman, right?
Yes, yes, exactly.
Okay. Okay.
And this will say how it's useful. Let's say we have this kind of you can say monotonically increasing function, right? So it is like as the value of x will increase, value of y will also increase. So the rank, right? So the rank for this data would be 0 for x and y, or let's say 1, 1 for x and y. The next 2, 2, 3, 3, 4, 4, 5, 5. So the x and y, if I take the rank, it is like having the linear relationship, exact linear relationship like this. If I take the rank, right? But if I take the data, even for this example, if I draw the graph, it would be something like this: 11, 12, then 23, then 34, 45, like this, right? So the data is looking something like this, some not linear relationship. But if I apply the rank and take the graph between the rank, it is linear, right? And that's why we are if we call if you talk about this particular graph perfectly increasing monotonically, like monotonically increasing function, then srcc, Spearman rank correlation coefficient, would be 1. but PCC would be just 0.88, right? So if you consider the rank, then we don't talk about this quadratic relationship. We what we care about is some correlation between x and y. Yes, there is some correlation, right? And that we can directly, you can say, get using the srcc, just using the rank, right? It's a very, you can say, simple idea, but it solved this problem, this quadratic problem. If the data is quadratic, the this pcc pearson correlation coefficient can be low, but there is a high correlation between x and y, so it is captured by srcc, right? And for this data, this say, uh, I have like a bunch of outlier here, 5 outlier here, but this PCC is very much, you can say, impacted 0.67, right? Because it will consider this much of variance here, right? And in this x direction, and this much of variance in y direction. Y direction, it is not impacting, but for x direction it is impacting a lot, just this 5 points, right? So PCC would be 0.67, but srcc would be 0.84 in this case, correct? As the value of x increase, y increase, and for some case it decrease also. That's why we don't have this exact 100%, correct? But there is some linear relationship. Perfect. This is some, I don't know why I have noted this, but this is one more, you can say, formula to calculate SRCC. I found this formula from, I guess, Wikipedia, or there was some solution notebook or assignment notebook of some university. So given the table using this di xi minus yi, you can calculate SRCC also using this formula. Okay, I guess the thing is over. Miscellaneous topic, we just discussed this yesterday. Continuous and discrete, uh, you can say, distribution, uniform distribution. Yes, the last that was mentioned in course video was variable distribution. That designing a dam and calculating the probability of, you can say, this event, disaster basically, which is a rare event, right? Once in 100 year like that, or once in a 50 year like that, right? That how to calculate that probability of some parameters, right? Some forecasting of this thing, rare events in nature. There we can use the variable distribution. So we know, like, what's the chance of getting this much of rain here, right? In worst of worst case, right? So we can use that, and this is very useful in like deciding on some values, like height of a dam. What should be the height of a dam? How much concrete we should use? Like how strong it should be, right? So this was discussed in lecture video. I guess the father of Srikant sir is like in civil engineer, and he was used to use this variable distribution. He mentioned, like, he said this story basically in our course video, right? Uh, this example: maximum rainfall in a day, right? Maximum, like maximum to maximum, how much rainfall can be happen, and what's the probability, like that. Okay, guys, any doubt or any suggestion or any, you can say,
So
ask
Mayur,
for this?
have you already covered PDF, PMF, CDF thing?
Yesterday
Yesterday.
fully.
Okay, I will look into that.
Sure,
And
sure.
would you be able to share this PDF which you are showing
Uh-huh.
notes?
It is uploaded on this drive already. It was there on a drive. I just renamed everything in order.
Okay,
Yes,
I
it's
mean,
already there. So if you go to the WhatsApp group and go to the description, there is a link. WhatsApp group description, there's a Google Drive link. So it has all the semester one, like all the three subjects.
It's
okay.
inside subject 2 and number 3. Statistics underscore 22. What is 22? I don't know. I guess it was a date, maybe, when I was
So,
creating.
what would be agenda for tomorrow? I mean, have you covered statistics completely? Because I'm a bit behind this time.
Hypothesis testing I have not covered, and I would not be, because I am not exact like 100% sure. So if you
Okay.
are not 100% sure, you can't teach it. That
Yeah,
I
yeah.
understand. So that's why I know like how it work out. But if you ask me a doubt, I want to be able to answer. That's why.
Mayur, we can ask to Sumanna if he can conduct a session on hypothesis because previously he had conducted it on beautifully.
Yes, let's ask like if
Sorry.
if he is available.
In the group, we can
Maybe I
ask
will.
him if he is free or
Sure, I will ask. Okay, guys. So, is there anything else? Otherwise, like whole statistics is covered except that hypothesis testing. So, okay, there was one topic that I decided for today. It's the revision of this combinatorics formula, right? With repetition,
Yes.
without repetition, like that. So, this would be useful. So, like your call, guys. So, should we discuss this formula tomorrow and start assignment? Not assignment that numericals, or should we discuss the formula today?
Maybe we will go ahead with we will revise it, and then tomorrow, once you are going walk you through us, then it will be good, I guess.
Okay.
I mean, that's what my point is.
Okay, others, guys.
And this is also there, right? Mayur, this one?
Correct.
Okay,
It's
okay,
all
okay.
also there.
Subject to
So whatever
exercise.
the important document I have, it's already on Drive or GitHub.
Yeah, yeah. Sure.
Yeah, so anyhow, it's 11:30, right? I think it's already
It's
been
around
Yeah, yeah.
two
11:30. So
hours.
better like
So it
tomorrow
doesn't make
we'll
sense
start this.
to continue more. Maybe people can just revise whatever happened as of now and go
Correct.
to